Hello and good afternoon, everyone. Today, inshallah, we will try to do a complete revision and overview on the topics that will be involved on our next midterm. The second midterm, it's really very important. It contains a lot of stuff. It will start from your knowledge in matrices as tools. You will need it as tools. Plus, starting from linear transformation, layer 2 of matrices, and of course vector spaces with all what we did study in vector spaces. Starting from a vector space, sub-vector space, combinations, how to get independence, basis, span, everything, coordinates, everything, okay? Even the last part. Also, which reminds me, the last lecture, it's really very important, which talks about the null space, the row space, the column space. It was really very good lecture, and I've solved a couple of problems in it, so it's really very important. You will have to see it. Okay. Of course, all our course resources and the recorded lectures, you will find them on YouTube, so you should be in a very good shape. شايف الحركة دي؟ Okay. Let's start with the overview, contents of the second midterm, linear transformation, layer 2 of matrix, and the vector spaces. I will start from some of the knowledge about matrices properties. Of course, all of you, I'm sure that all of you master the relations in matrices. We already had our first midterm just focusing on the propositions of matrices, the inversion, the transposition, the multiplication, and everything else. Okay, you will need those reminders just to refresh your information. If we have a square matrix A and the k belongs to it, which is and the k belongs to the set of natural numbers, I have a to the power of k equal 8 means a times a. Of course, in the previous exam also, we covered the idempotent matrices. Do you remember what's the idempotent matrices, Omar? It's the type of matrices where a equal to a to the power of 2. We had a very nice problem in the first exam. Also, conventions that a to the power of 0 is equal to the identity matrix. Of course, you know what's an inversion. We will need this either to get the inverse using Gauss, okay, elimination methods, or various Gauss elimination methods. And in here, it's not going to be, he is not going to ask you about to find the inverse of a matrix, but you will use it if you need it. So you need to review the inversion. Of course, A times B is equal to I, means B is an inverse for A, and the AB is equal to BA. A is equal to A minus 1. I'm sorry, A times A minus 1 will equal to the identity matrix. Not all the square matrices are invertible, only those with singular matrices. What's the singular matrix? A singular matrix is a matrix whose determinant doesn't equal to 0. Okay? Once more, what's the elementary matrices? Do you remember what's an elementary matrix? Do you remember what's an elementary matrix? What's the elementary matrix? Elementary matrix with one of the operations which grows or multiplying grow by number. Yes, exactly. Perfect. It's the same order performing the same elementary operation. Let M be a square matrix, then R, S, and Z, and let M be invertible matrices of the same order. So you know that M to the power of R times M to the power of S is equal to M to the power of R and S. Are you sure the projector is okay? Do you need me to change it just a little bit about the contrast and the resolution? Huh? This is better? Better? Okay. So once more, M to the power of R and all of them to the power of S is going to equal to M to the power of R of S. A minus 1 of minus 1 is going to equal to A, so an inversion of an inversion is equal to the same matrix. If I have A times B and we have the negative 1, remember that we switch the order and also we will do the inversion. So AB, the power of negative 1, equal to B minus 1 times A minus 1. If we multiply by a constant, it's going to be a k to the power of negative 1 times a to the power of negative 1. A transpose inverse equal to the inverse of the transpose. So all of these relations are really very important. The propositions for each elementary matrix, you know that this is the first operation, then the second operation, then the third operation applied. Okay? Remark the order, review the order of using elementary matrices. As I told you previously, this is not going to be the main of our exam, but I need you just to review quickly those couple of problems that we're talking about the elementary matrices. Of course, if I have A, then we will perform the first elementary, second elementary, blah, 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 and it's equal to N. So the elementary matrices are E1, E2, up to EK, all of them are the inverse. And of course, if I moved them to the other side, the A matrix will equal to replacing the order and having the inverse of each elementary matrix. And we really did that plenty of times before the first method. Okay, very good. This is all about the inversion and how to get the inverse using the elementary matrices. On this slide, those are equivalent. The rank of A is equal to n for square matrix. It's exactly like the reduced echelon form will reach a unique matrix. It's exactly like having a unique solution in a system of equations, if you remember. A is invertible. A can be written as a product of elementary matrices. As I told you, it will give you a consistent independent, which means a unique solution. So all these propositions are the same. Now, I want you to remember the second or the first topic in specific in our next midterm, which is called linear transformation. I believe in the first midterm we had the opportunity to see one question about linear transformation. But here you can see more than one question in the core of linear transformation and in the inversion of a linear transform. Okay, so I need you to review it. Of course, if I am moving from Rn to Rm, that's a linear transform. What's the linear transform? Second time, it moves stuff from the Rn dimension into the Rm dimension. The matrix of the transform, which transform objects from n to n, it's gonna will be with the dimension m by n. So this matrix dimension, remember my words exactly, this matrix dimension will be m by n. Do you read me? This is the transformation matrix. So the transformation matrix will be the transform in general. T of x will equal to the transformation matrix times the column of vectors, which is input. It's going to be the input of your transform. So the input is going to be n dimension. So the x should be an n times 1. That's the dimension. And for A of t, it will be m by n. Now all the dimensions adjusted well. This is important and I wanted to keep it in mind. Okay? Okay, for all x belongs to Rn, as I told you, in that case the matrix AT is unique and it's called the transformation matrix. I want you also to remember, and this is really very important, Mr. Hazem, how we can get the transformation matrix. We can get the transformation matrix by three ways. Okay? So for this example, this is not a new one, but I prefer to use it for you in order to be familiar with it. He told you here, how can we find the transformation transformation that moves from R3 into R2? What's the gain here from R3 into R2? My transformation matrix will be 2 rows with how many columns? 3 columns. Okay, perfect. How to bring it to life? How to get it? I have 3 ways. The simplest is to look to the function if it is given. This is the function of the transform given to you, Ya Omar. So if I look to the function of the transform, I will remark it has 2 coordinates. I have 2 coordinates. Look to the missing ones. So now the first row, I will perform the transformation matrix by rows. So the first row will be 1, coefficient of x1. There is negative 3 and 0. So it's going to be the first row 1, negative 3 and 0. The second row, how it's going to be? It's going to be a 0, 2 and the negative 4. This is how to perform it by rows. I can perform it by columns. And it's very simple. All I have to do is to write these two components as a column, as columns. So it's going to be x1 minus 3 over x2. And for the second row, I have x2 then minus 4x3. I can write the transformation matrix very simple by columns. The first column contains x1 element 1, but it doesn't appear down, so it's going to be 0. For the second column, it's going to be same way like. It's going to be a negative 3 and 1. And for the last column, it's going to be a 0 and negative 4. That's how to write it in columns. So I can write it rows or write it columns. And there is also third way. What's the third way, Ammar? Yes, I will use the columns of a unit matrix from the dimension of the input. The input here is R3. So the canonical vectors are 1, 0, 0, 1, 0, 0, 0, 1. All I have to do is to make a substitution in these two components. First by 1, 0. Then it will give you the first column. Then 0, 1, 0, it will give you the second column. Then 0, 0, 1, it will give you the third column. Okay, let's do it fast. In order to do this, given the general expression that defines the linear transformation, the dimension is, this is from R3 into R2. So I'm expecting that the matrix will be 2 by 3. Okay, perfect. Second step. These are the two functions. So I can really easily write them as a matrix. Okay, from the matrix, if I want to go for rows, it's going to be 1, negative 3, and 0. That's the first row. Second row will be 0, 2, negative 4. This is if you want to write them as rows. 1, negative 3, and 0, 0, 2, and negative 4. If you want to write them as columns, perfect. This is x1, but there is no x1 here. So as a column, it's going to be 1 and 0. If I move to x2, Mr. Muhammad, I will remark that x2 element is negative 3 and x2 is 2, so it's negative 3 and 2. Then for the third column, there is no x3, so it's a 0 and a negative 4. So I can write it rows, I can write it as columns, as you can see, I can write it as rows and as columns, and also I can use the elements of a unit matrix. So I will insert 1, 0, where I will substitute 1, double zeros for x2 and x3 to give you 1. Then 1, 0, which is going to give you zeros. So the first column is 1 and 0. That's 1 and 0. I will do exactly the same as 0, 1, 0, which will give you the second column, 0, 0, 1, give you the third column. This is how to get your transformation matrix. Any questions? Of course, we did go through this plenty of times. اتفضل يا فندم.
هو ممكن يجي بالخمس اسابيع اللي هم كانوا في الترم الاول
ما هو ده انا قلته في الاول.
ايوه بالنسبه لقد ايه؟
ما اعرفش. لان اللي قبل كده ده بتستخدموا تولز.
ايوه
لكن مش اسئله مباشره.
والله بكيفنا
يعني مش هيجي يسالني مثلا
بكيفي. ما هسالك في ايه؟ ما انت اللينير ترانسفورميشن انت عارفه. بس بص بقى للديفينيشنز بتاعت اللينير ترانسفورميشن ولين توف والجزء بتاع الفيكتور سبيسز. هسيب دول وهروح بقى اسالك على مالتيبليكيشن ماتريسيز او على اليونتري ماتريسيز. لا بس انت اصلا الشغل كله زي ما هنشوف دلوقتي قايم على الجزء اللي فات معايا يا عامر.
ايوه يعني هو
انا جاوبت.
طيب يعني المعظم هيكون على الاسابيع اللي هم معانا في الترم اكيد صح؟
طبعا اوكي. طبعا انفولفنج ده معايا عامر.
ايوه
يعني من اول هنا في مفهوم من اول هنا لغايه اخر المحاضره.
يعني من اول الترانسفورميشن.
على فكره انا جاوبت لينير ترانسفورميشن. افهم ليه قلت لازم جدا لينير ترانسفورميشن لين توف فيرتوال سبيسز.
السبيس ده
كامل.
الاسبوع السابع
كله
هنكمل بقى لحد اللي هو كمان.
لغايه ما انا وقفت المحاضره اللي فاتت. اوكي. So let R into R be a linear transform. So the kernel ده مهم. انا بس عايزك ايه تمشي ورا. حاليا امشي ورا. بعدين راجع بقى الليكتشرز دي تاني وانت قدامك كذا الوقت بتاعك. لكن انا حاطط لك كده 110 سلايد. متضمنين غالبيه بس طبعا ده ما يغنيش عن الاصل. كلامي واضح؟ عارفوا فاهميني؟ اوكي. Let Rn into Rn be linear transform. يعني ايه kernel of transform? What's the kernel of T? Denoted by KT. It is the set of vectors in Rn which are mapped into mean. خلي بالك ان ده لسه معايا تاني kernel في اللاست lecture. اوكي. يبقى الكيرنل of T it is x belongs to Rn such that the linear transform is equal to 0. And from here I can get the conditions and I will know down the road how to get the vector space of the kernel and the dimension of the kernel. So now we introduce the kernel. What's the kernel? The kernel is simply your linear transform is equal to 0. And I try to find or to solve the system Ax is equal to 0. Okay. The range of T denoted by range T in the set of images through T, and T of X is a subset from R of M, which is a sub-vector space from R of M. So this slide will be connected later with vector spaces. So it's an important one. Okay? If T R N is an N transformation, the following conditions are bold. Look to these three conditions and tell me what does it remind you of. Look to these three conditions. This is linear transform. The first condition is talking about an addition. Am I right? An addition between vectors. Am I right? And after transformation, it's equal the same, which means Mr. Hazel a closure in the addition process. Okay. The second is talking about multiplying a vector in the linear transform by a constant value. Am I right? And also it has a reflection with vector spaces. If you look, Mr. Ahmed, to the last one, it is the transform of the origin which reflects to you by the origin. That's, you have an addition closure, multiplication by scalar closure, and an origin. Doesn't this remind you of something? In vector spaces down the road. So it's like he's introducing the stuff that you will need down the road. But now you know this is going to be reflected down the road. Of course, Rn to Rn is a linear transformation. I want you to notice that I can write AT if it is multiplied by x1, x2, and xn, the column. I can separate it to be A times the first vector times x1, the second of the canonical basis times x2, and then it can be arranged there. Because x1, x2 up to xn are all constant scalars, so I can take them out. So actually, they can be put on this form. This is the transformation matrix times 100, which is going to give you the vector after the transform times x1, and also for the rest of the columns. I want you also to remember that T from Rn into Rn is completely determined by the images of the columns of the identity matrix. This is why when we are trying to get the transformation matrix, we use the row, use the columns, and we use the elements of the unit matrix, which are the canonical basis. Okay? 1, 0, 0, 1, 0, and so on. Proposition. If I want to get an inversion for a linear transform, not all the linear transforms are invertible. There is a condition in order to invert a linear transform. What's the condition? You should be moving from the same dimension. So I'm moving Rn into Rn. You understand what I'm saying? Okay, so that's a very good condition or very strong condition, which means that you can invert you can find the inverse of your matches. I put this example, also it's one of the previous examples that we had previously, but I wanted to make you remember how we do the inversion of a transform. So once more, if you look to this transform, which map R3 into R3, it's moving from R3 into R3, am I right? Okay, how it's going to be moved through this function? You have three components, Omar. So the first component, I can write the transformation matrix, just like that. The first row will be, anyone to tell me the first row?
0,
1, 1. The second row will be 2, 0, 0. The third row will be 0, 0, 4. This is by rows, and by columns is going to be the same. Or I can use 1, 0, and it will give you the first column. 0, 1, 0, it will give you the second column, and so on. Okay, done with it. This is the, if I'm using 1 zeros, 1 0 0, 1 0, sorry, 0 0 and 1, it will give you the columns of the transformation matrix. And it is exactly the same as we all found out or find out previously. Okay? So that's the matrix that I want. I want to get the inverse. So I'm moving from R3 into R3. So if I want to get back, I will have to get the inverse of this matrix. You know how to get the inverse. Either by the cofactor method or using Gauss elimination. Do you remember how to get the inverse? عامل. هنا أنا بسألك على الانverse. You are using the inverse from your background. Okay? It's not a question about the inversion. Okay? Direct question. But you will use it from your previous knowledge. Okay. I've already succeeded in getting the inversion. So that's the inverse matrix. So look at it as I'm here in R3, moved to R-3. If I want to get back, I will use this matrix. So this matrix is for going forward, and this matrix is going backward. Do you read me? Of course, that's the inversion. Now T is invertible, and the area transformation T minus 1 is defined by this matrix, and that's the function of the inversion. That's the function of the average transform. Very good. Now we will go to the second topic that will be covered in our next exam, which is Lien-Tooth matrices. Okay, Lien-Tooth matrices is one of the very good applications on a linear transformation, on multiplication of matrices, on the inversion, on all of this. Also with a very nice touch to the input, or usually with the microeconomics. The main equation that we use in Lien-Tooth matrix is X, which is the production, is equal to the total demand. So X, the production, the units that you produced, should equal to the total demand. The total demand is distributed between two types of demand. The final demand and the intermediate demand. Yes, you are right. Okay. A is the technological matrix, and we already had previously how to bring it to life. X is the production, and the D is the final demand. Of course, this slide also, one of the previous slides, I thought to bring it to you here just to refresh your information. The basic idea behind Lien-Tooth's model in macroeconomics describe how different industries or sectors of an economy depend on each other. There is an integration between the various sectors in an economy, okay? On each other for input and output. Each industry both produces goods, which is the output, and uses goods, which is the input, from other industries to produce its outputs. Suppose that we have in industry sectors in an economical system, so the input and output technology matrix is denoted by A, and for each element of A with I and J, which is related to the number of productions and the number of sectors and goods that you are producing. AIJ, the amount of output from each industry needed to reduce one unit from the output industry J. A column J tells you all the inputs required from other industry to reduce 1 unit in industry number J. Of course, the definitions, X in the production, AX intermediate, D the final demand. This is, if you remember, this model of 3 sectors, and that's the free market or the final demand. If you remark about the arrows and you know about this lecture, please do review it. It's a really, very important lecture. Now I know the model. X is the production, AX intermediate, and the D is the final demand. For your example, just to refresh it quickly, we will let A, which is the technological matrix, remark from the technological matrix that the elements exist here are all positive. You will find non-negative elements. And he is telling you in the matrix of technical coefficients of an economy with how many sectors? 2 sectors. Just only 2 sectors. X, the vector with the production of each sector, and the D, the vector with the final demand for the goods produced in each sector. Considering the entity of X equal to X is equal to D, I can find the intermediate consumption. How to find the intermediate consumption? I will multiply the matrix of the technical or the technical coefficients times the production. All I have to do is to multiply the matrix by, okay, معايا شباب, by the production. So I will multiply this matrix, this is the A matrix, by the demand, by the X column, which is the production 40 and 12. If I multiply them together, I will get the intermediate demand. So this is the intermediate demand. What's the intermediate demand once more? It is the demand from the production that will be needed inside the process. How to get the final demand? It is the difference between the production and the intermediate. So it's really very simple. شكرا يا عامر صح؟ طبعا to the definitions. If what's the amount of the final demand? It's very simple. I will get the production, which is 40-20. And I will subtract from these values 20 and 12, and then I will get the final demand, as you can see. You will see later some other problems about Lintoff matrix. Okay, what's the inverse of Lintoff matrix if you still remember? It's I minus the technical matrix to the power of -1. That's the inverse of Lintoff matrix. And why it is important? It's important because it will give you the required production to satisfy certain demand. So this is the really very important. It will give you the production based on the demand, the given demand. And also it's a measure. I can use it as a measure of the effects of the demand of one vector, of one sector on the other sectors. That's the importance of the inverse Lintoff matrix. So simply the inverse matrix is I minus A to the power of -1. If A have, this comment is really very important, A and D have non-negative entries. And if each column sum of A is less than 1, then I minus A to the power of -1 exists and has non-negative entries. Look to this example, it's really important. I've given you the inverse Lintoff matrix. You have inverse Lintoff matrix. So you don't have to bring it. I have an I minus A to the power of -1. That's the inverse Lintoff matrix. Usually I will need it if I told you if one monetary unit increased in one sector, what's going to be the effect on the other sectors? And that's one of the classical questions in this part. So you should remember it very well. So once more, all I have to do is to multiply for the first sector the inverse Lintoff matrix in 1.0, which means what's the effect of having one monetary units from the first sector on the total economical system that you have. So all I have to do is to multiply this guy in that matrix. And the result will be 2.5, 0.83, 0.83 in this case. Those numbers, if you add them together, it will give you the total production increase, the total required increase in production due to how many units monetary? Just one. In which sector? The first one. If I want to see with the second sector, I will use 010 because this economical system consists of how many sectors? 3 of them. Okay? So all I have to do is to multiply this matrix by 010. This is, I'm talking about good number 2 or second sector. This is, as you can see, that's the effect of the production of increase in demand for the second sector on all sectors. And also, that's the third one. If I want to determine which one is more effective on the economical system, just look to the amount of the total production increase. If you look to those numbers, then the largest effect is going to happen with the first sector. So if you have one monetary unit increase in sector 1, this is going to be more dramatic on your production compared to the other sectors. Are you with me? Okay. Of course, this is also already answered in specifics, in specific the effects of having an increase of one monetary unit in any of the various sectors, and these are the results. And so you can use whatever. The previous two chapters will be involved in our midterm, and of course, this guy too, which is very, very important, which is about vector spaces and sub-vector spaces. Don't you feel relaxed once we get to vector spaces and sub-vector spaces compared to the two previous ones? Because we spent the last I'm talking about myself, because the last 3 weeks, okay, or 4 weeks, we were talking mainly about vector spaces, okay? So the others look like a history. What's a vector space? Anyone can define a vector space? It's a non-empty set of vectors, yes? Under how many conditions?
Yeah.
2 main conditions: addition, closure, and the multiplication by scalar closure. And all of these information from the first 5, which are the 5 information, that's the definition. That's the definition of the addition process. But it will satisfy the summativities, the distributivity, the commutativity, the existence of an origin, the existence of the symmetry. What's the symmetry of an element? The symmetry of an element. What we mean about the symmetry of a vector. If I have a vector, the symmetry is going to be exactly the same coordinate, but with negative values. That's what's called a symmetric vector. And the adding them together will give you a 0. Of course, the other 5 properties are related to the multiplication by scalar, and this slide we repeated plenty of times. Even in the last revision, I don't remember, but I still remember that I made a recap with this slide previously. Of course, what are the requirements of a subvector space? The requirements of subvector space are 3 conditions. Do you still remember them? Addition, closure, multiplication by scalar closure, and the 0 of your subvector space is the 0 for the main vector space. Okay? They must join the same origin. Are you with me, Mr. Muhammad? Okay. So let V be a vector space and W be a subvector space for V. W is said to be a vector subspace for Vf. We have these 3 conditions. Also, I want you to remember that every subvector space is itself a vector space. Once more, every subvector space, it is by itself a vector space of itself. Okay, but it's a subset from a bigger vector space. And every vector space is a subvector space from itself. These 2 definitions are given here. A vector subspace of a vector space V is a vector space. And the vector space V is a vector subspace of itself. Okay, if I have U1, U2, V2 vector spaces of vector space W, then their addition is a subvector space. Their intersection is a subvector space, but their union, it's not necessarily to be a subvector space. So now I have 3 relations, which is really very important, Mr. Muhammad. I have, if I have the intersection between 2 subvector spaces, it is a necessity to be a subvector space. If you add 2 subvector spaces from certain vector space, the result will be subvector space. But the union, not necessarily, is a subvector space. It will be a subvector space if these 2 subvector spaces are subsets from each other. But other than that, it's not guaranteed. Are you with me? Okay, I want you to know the differences between the intersection, the union, and the addition of subvector spaces. This is why I dedicated and I borrowed this definition from FCT. It's really very nice. Okay, so in linear algebra, the concept of intersection, union, and set addition are related to the operations. The operations of intersection, union, and addition. If I'm going to talk about intersection, what do you feel when we are talking about intersection? The combined, the shared vectors. The vectors or the set that belongs to both sets. Of course, the set that will belong to two sub-vector spaces, at least it will contain the origin. ما هو اي sub-vector space لازم يبقى فيه origin. يبقى sub-vector space ده فيه origin, sub-vector space ده فيه origin. Once you get their intersection, at least you will have the origin. This is why it's a sub-vector space. Okay? So once more, X and A intersection B means X such that X belongs to A and X belongs to B. Intersection meaning definition of two sets devoted in the set of elements vector that are in both A and B. These are the intersection of A set vectors are shared by both two groups. Intersection meaning, of course, these slides are shared with you so you can read it. I don't want to lose time in reading them with you. You can go through them. But for a quick example, if I have a 1, 0, and 2, and 0, and the 1, 0, and 3, and 0, so the intersection between these two sub-vector spaces will be 1. That's an example to show just to refresh your information about the intersection. If I'm talking about addition, and also before we complete, or before to move forward, the intersection, okay, doesn't change the type of the dimension of your subvector space. Doesn't change it. It's just taking what's combined between them, what's shared between them, okay? Once we go for an addition, Ya Omar, this is the addition of two subvector spaces. In the addition of two subvector spaces, remark has it that the construction of the vectors will change. Construction of vectors will change. Okay. A definition is context of linear algebra refers to addition of two sets of vectors, then often vector spaces or subspaces, not the individual vectors. So, remark, when I say A as a subvector space plus B as a subvector space, I will get new elements, which is A plus B. Where A belongs to A capital and B belongs to B capital. I usually, of course, you have all the definitions with you, so you are in a very good shape. But this definition is very important. Or this example. Look, Mr. Muhammad, I have the vector subspace A with the image or the